Well, now let's finally get to the thing that we've been doing all of this work with S and T shifting for, and that is to solve differential equations that have discontinuous inputs. So let's start with something simple. Y double prime plus 9y is equal to 4 times the Dirac delta function evaluated at t minus 5. The initial conditions are y at 0 and y prime at 0 are both 0. So we have either, if you want to think of this in terms of physical system, say a mass spring system, it's at static equilibrium. It's just sitting still. And then at time 5, it gets hit uh, in some way that suddenly imparts energy into the system at a magnitude of 4 units. So we would like to know how this system responds under those conditions. Intuition, of course, would tell us this. This has no damping term. So all you're going to get out of this is, as long as you stay within the physical limits of the system, is simple harmonic motion. We're going to have a sinusoidal output, but it won't start running until time t equals 5. So we do expect a unit step function to be coming up here some way. So to turn on that sinusoidal response at time t equals 5. But let's solve the differential equation and see where all that comes from. Now, we need to use our formulas for the transform of the derivative of a function. So we know this, that in general, the derivative of y prime is s cap y at s minus little y at 0, and the transform of y double prime is s squared y at s minus sy at 0 minus y prime at 0. So we're going to use those to transform this right here. So all of this gets copied down as the transformation of that first term of the equation. And of course, if you are looking at the initial conditions, you know a lot of that's going to just drop out here in a moment. And then the transform of 9 y at t is 9 times cap y of s. And then I've got 4 times the transform of delta t minus a. And the transform of delta t minus a is e to the minus as. So there is the transform version of my initial value problem. Now, y at 0 and y prime at 0 are both 0, so these two terms drop out. And we have s squared plus 9 times y at s is equal to 4e to the minus 5s. And then we divide through by that. Y at s equals 4 e to the minus 5s over s squared plus 9. Okay, well, we're just going to do exactly what we did on the previous examples and say, well, let's focus in on things one at a time. That s squared plus 9, that is going to go back on the t-axis to either a sine or a cosine. Since I have a constant here rather than an s, this is going to go back to a sine. So y at t, well, I know that it's going to involve a sine. And that is 3 squared, so it's going to involve sine of 3t or some such thing. Now, we have a coefficient of 4 here, so that will just go along for the ride. And finally, we need to deal with this e to the minus 5s. That is our first shifting theorem here. If you have e to the minus as multiplying your transform, then that induces a right shift on the t-axis of a units as well. So u t minus 5, and once again, not quite enough room. So let's rewrite that. 4 u t minus 5 sine of 3 times t minus 5. So there is the solution of the ordinary differential equation. And I'd like you to think for just a minute about what we've just done. This equation right here, we have studied a lot of methods for solving differential equations so far in this course, and not a single one of them can handle this. This is a non-classical function. It's not only discontinuous; it's not even a function in the classical sense. So we have no methods up until now to address this problem. But now that we can use transform calculus, we find out that it's actually not an especially difficult problem. It just involves knowing how to transform that impulse function and then knowing how to take the inverse transform when you have that exponential multiplying your fraction. So there is a great start, and let's do one more, and that'll give us a good sense of how this works.